Hi, everyone. Welcome to our webinar series, Reduce Risk with Risk, Designing and Maintaining Secure Embedded Linux Devices with Advantech Risk Platforms. I'm Teresa Kisha, and I am, again, your host for today's session. With me today, I have from Timesys, Maciej Halasz, Vice President of Technology, and Akshay Bhatt, Security Architect. We also have with us today Jason Zhu, Risk Product Manager at Advantech. Today, we move on to session 3 of this series, leveraging open source software to protect IP and data on the device. Before we begin, I'd like to take a minute to mention a few things. First, this session is being recorded and will be available post-event. The link to the recording, along with the link to today's slides, will be emailed to everyone within the next business day. Next, in order to keep things within the time allotted, all attendees will be on mute during the presentation. Following the session, we'll have a 10 to 15-minute Q&A to answer questions that you might have. If you would like to ask a question, simply post it via the questions window panel, and one of our presenters today, either Maciej, Akshay, or Jason, will answer it during the Q&A. And finally, after today's session, one lucky attendee will receive an Advantech RSB 4411 SBC, Compliments of Advantech. Everyone in attendance today will be automatically entered into the giveaway drawing for this session. The winner from today's session will be notified via email. So with that, I'd like to say good luck to everyone, and I'll now hand control over to Maciej to get us started. Thanks again, everyone, and I hope you enjoy today's session.
Thank you, Teresa, and welcome back, everyone. I'm glad that you could join us today again. I'm going to start today's sessions by just recalling some of the topics that we've discussed during session 2. We have focused during session 2 on software authenticity. How do we verify that the software that runs on a device is authentic, that comes from our company, that it's our application, that it's the software that's supposed to be on the hardware. So we've focused on software signing, image signing, as a way to verify the authenticity of the software. We have also discussed the fact that the software authenticity, the signing of the software, has to be backed by some sort of hardware features. And the Advantech's hardware that's equipped with NXP's processor provides a lot of features that assist with security. And we've discussed specifically the use of one-time programmable fuses last time to store the keys that are used for verifying the signatures. And we've also discussed the use of ROM as a first software that can be used to verify the signatures themselves. We have also talked about the chain of trust, because building a secure device means that I not only have to authenticate the first level software, but I have to extend this authentication of signatures to higher software layers. We have also talked about the fact that when you think about building a device that requires security, it's always best to identify those requirements early on in a project, because in many cases, implementing security means design modifications, design changes. So if those requirements are identified early on in the process, you can avoid having to use more of your time to do a redesign. We have also talked about Advantech hardware a little bit last time, and it's very easy to use Advantech systems and implement security. Access to one-time programmable fuses is straightforward. It's easy to implement signature verification. We've also mentioned towards the end of our session the use of trusted platform modules as another way of protecting keys that can be actually used in addition. We haven't focused much on that topic because we've run out of time, but my colleague today is going to take us through a little bit more on the topic of a TPM. Lastly, I wanted to highlight again that Timesys Trust team of trained security experts is available to work with you on your projects, whatever your security requirements might be, whether that's authenticity or encryption or other aspects of protecting data. The trust team from Timesys can help. With that, I'm going to hand the control over to Jason Zhu of Advantech, who's going to take us through Advantech's hardware information, and he's also going to discuss some of the markets where Advantech's hardware is used with security.
Hello guys, this is Jason from Advantech. I'm in charge for the risk platform, and today, who didn't show up in the last two sections, I will give you a brief introduction of what Advantech do and what's the relationship between Advantech and Timesys, and we're trying to everything we could to reduce the risk on the risk product. And as you see on the slides for Advantech side, we do have a different form factor of product for the board level, for the cases, for the gateway level. Also, we are releasing all the things like wireless. We can bundle things with wireless modules, with display, with all the connectivity, with storage. And for the software side, Advantech risk product are released along with the standard evaluation key called EVT. We call EVT to evaluate performance and stability. The EVT also is a software development platform for developing application in early stage. It includes complete image test program, utilities, SOP, so customer can verify software and hardware compatibility very easily. We also offer a complete solution package, include BSP, bootloader, middleware, like we call SUSE API, and a corresponding document software development guide, API illustration, and driver list. So customer can get all the information and source code they need from Advantech and from Timesys. All the standard offering are free of charges. Right now, furthermore, we are now cooperation with Timesys. We are capable of doing like all the build engines, custom OS, driver porting, and more importantly, we are focused on the security things right now. We are offering the security notification. We're offering add-on value for secure boot, and I think actually we'll talk about more in the next couple of slides. Data protection. Everybody knows data is very important on all the vertical markets. From a hardware perspective, we have project with CD kiosk. CD are working on things like public Wi-Fi, better traffic management, driverless CD buses, and a kiosk, and connect people with CD events. And in a time where data can be breached by hackers, or the backdoor left open for data thieves to walking and ransack the place. Some people are sounding alarm on smart city because we're concerned about data privacy. So city kiosk and smart city is our one vertical market, like really need a data protection on this one. Of course, the government. We don't talk about much, like all the governments need all the security, like high level. Third one is medical. Some in the recent like couple years, breaches and identity theft involving medical data are on the rise. According to the Phonemion Institution, criminal attacks in healthcare have increased by 125% since 2020. I think 2010, sorry, and now a leading cause of medical data breaches. So the study also found that 91% of healthcare organizations has experienced at least one data breaches, costing more than $2 million on average per organization. So right now, for my past experience with the medical customer, they are more and more focused on data protections right now. Like almost like 80% require TPM or any software protections. The third one, the fourth one is we all know about the military. Military have very high standard of the security things. We have been recommending all the government national security IT system make use of TPM, hardware-based system security features. Also, which is also wide available on the enterprise-grade tablets and laptops. Is a microcontroller that security store. Everybody knows stores encryption keys, password, and certification. So basically, for Advantech except for hardware side, in the past like couple years, we have a lot of inquiry for the security for data protection for different vertical markets. Here's the computer module like Advantech offer. At this moment, we are cooperating with Timesys. Of course, we pay more attention on the Dynamics 6 platform, since they are more like flexibility. They have very high end using also the low end, low power consumption solutions. So we pick Dynamics is our key things to move forward and and in the future we may work with work on the Dynamics 8, but right now we just focus on the Dynamics 6. And here's a different form factor we're offering RTX, which is Advantech proprietary form factor especially for ruggedized solutions. We offer the most popular form factor Q7 and Smart modules in the market. And also in the next slide, we are doing some like single board computer things, RSP6410 and RSP4411. So basically, we offering different type of we are offering from board level, even for gateway. We all have all the form factor available hardware from hardware side. And Advantech and Timesys is not just an ecosystem partner. We are bundling together. We are like from Advantech. We are offering the longevity, like best longevity, the best revision control in the market, and we're also doing all the designs in service. And from Timesys is the best on software side. We have been working with Timesys for a lot of projects. The ODM project, the standard of the shell project, like bundling service, like really big customer. They are very good on security solutions engineering service. Also, they offering a very fast support. So we are not just ecosystem partner. We are like bundling together. So thank you. That's my slides right now. We will pass the control to Akshay. Actually, you are now has a control for the presenter.
Hi everyone, this is Akshay from Timesys. So today we're going to talk about IP and data security, and in particular, how do we protect data at rest, how do we protect data in use, and how do we protect data in motion. So we're going to talk about encryption schemes, how do we secure the key which is used for encryption, and then how do we protect the data which is being used in runtime using like Arm TrustZone and a secure operating system called Opti. And lastly, we're also going to talk about trusted platform modules. So this is a slide from last week's presentation in which we concentrated on secure boot. So today we're going to concentrate on data security. And the concentration is going to be like on secure by design. So during the product development lifecycle, the goal is to try and harden the system and secure the system as much as possible. And then once the product is deployed, it mainly goes into the maintenance mode, in which you just monitor for CVEs and patch any CVE fixes. So when we talk about data security, there are two key aspects. One is confidentiality. So let's take an example of like a medical device in which there is patient data being stored on the device. So for compliance reasons like HIPAA compliance, you might want to protect the user data. And one of the ways to achieve that is using encryption. The other use cases might be your device might be running like a web server, in which case clients connecting to the web server need a secure connection. And to achieve that, you'd be storing private keys and certificates on the web server. How do you protect these keys and certificates from getting tampered such that the network communication is not compromised? And some other customers have needs for IP protection, so that like their algorithms are not reverse engineered, or somebody doesn't like just copy the flash memory and put it on another device and then sell counterfeit devices. So all of these are security threats and have different mechanisms in which we can prevent either loss of IP or breach of user data. So, and we're going to talk about different techniques to achieve the same in this presentation. So protecting data at rest, the easiest way to achieve that is by encryption. You can encrypt either the full system or just like a partition. We're going to talk about more details in the coming slide. Here's this slide is meant for like a high-level overview. So when we talk about data in motion, it basically means like if there is a server and a client kind of a model in which the client is talking over a network to the server, how do we secure that communication? It's mainly done using like certificates and authenticating the server and the client, and then establishing secure communication channel using like SSH or TLS. Lastly, protecting data in use. This is if somebody tries to sniff the DDR memory bus, we can use like processor-specific encryption schemes, or if your Linux kernel gets hacked into and somebody gets root access, how do we still keep your data confidential? And that is achieved by using like Arm TrustZone. And we're going to go over more details in the coming slides. So the first one is protecting data at rest, and it is achieved using encryption. So on i.mx6 platform, there is an option for encrypting the bootloader, and you can extend that to the kernel. And using some open source technologies, you can extend that to the root file system as well. So depending on what you're trying to protect, you'd select a scheme appropriately. And the encryption scheme used is called symmetric key cryptography. Basically, it uses AES. Symmetric key cryptography means that the key which is used for encryption is the same key which is used for decryption. What that translates to is you take your software and then you encrypt it using a particular key on your build machine or your host PC, and then flash that encrypted software onto the device along with the key stored on the device. And the device, when it boots up, it decrypts the image using the same key. This way, if somebody were to look at the flash memory, all they're going to find is like an encrypted image. How do we protect the key then? To perform that, you need to use like a processor-specific mechanism, and this mechanism is available on i.mx6. i.mx6, each of the i.mx6 processors come with a unique key pre-programmed by NXP at their factory. So to go over the details, as I said, you take like your bootloader image, and then you generate a secret key, which is used to encrypt the bootloader image. Once you encrypt the bootloader image, then the way you protect the secret key is during your manufacturing process, you take the secret key and using either like the U-boot or the kernel, which has some functions available, you would encrypt this particular secret key using like the one-time programmable key, which is the master key pre-programmed by NXP, and you append this particular encrypted secret key onto the encrypted software image, and then burn that into the flash. The encrypted secret key is also referred to as key blob. The one-time programmable master key programmed by NXP itself is not accessible outside of the processor. And since only signed software can run on the device if you enable secure boot, nobody else can go ahead and decrypt this key blob to get the secret key. During runtime, what the first step is, like the ROM looks for this particular key blob, and then it decrypts, assuming the software is signed and all of that passes the verification. It then goes ahead and then decrypts the key blob to get back the secret key, which was generated by the user. And then it uses that particular key to decrypt the encrypted software image, such as U-boot. Once it does that successfully, it goes ahead and jumps from the ROM code to the U-boot code, and the device continues to boot. So this mechanism is great for encrypting U-boot and the Linux kernel. When it comes to the root file system, your root file system might be a large root file system depending on your application, and you might have like a 2 gig root file system. If that is the case, decrypting that during boot time is going to be very expensive in terms of the time in which the device takes to boot. For that, you have another option called dm-crypt available in the Linux kernel. And what that does is it allows you to do block level encryption of either the entire root file system partition or like user data partition. So you can select what to encrypt. And this particular feature is widely used in most of the major Linux distributions and Android. To go into more details as to how this dm-crypt works is you have your ROM code which loads U-boot, U-boot then loads kernel, then goes ahead and then jumps into a initramfs. The initramfs is basically responsible for unlocking your encrypted root file system and then mounting it. And to unlock the root file system, it needs to know the key. The key itself, in case of like Android, is basically your PIN number or the screen pattern which you enter. So you can have like a user input to encrypt your root file system, but in standalone embedded devices, that is not practical. So you need another mechanism to store the key securely. One such mechanism is to store it on an external TPM, or like in the previous slide, we talked about like a key blob in which like we can generate a secret key and use like the i.mx6 master key to encrypt the secret key to generate a key blob. So we could use a similar technique and then store the encrypted key blob in your like boot partition, and the initramfs can go ahead and then decrypt that on the fly and use that to decrypt the root file system and mount the root file system. Here's a quick overview of that, where like the root file system itself gets encrypted using a file system encryption key, and the key which is used for the file system encryption gets encrypted using the i.mx6 master key, and this happens at your manufacturing or the production facility. And during boot time, it just does the reverse, in which the encrypted key blob gets decrypted and to get back the file system encryption key, which is then used to decrypt the root file system. There are also other mechanisms available if you're trying to protect the data in flash. So if you don't want to encrypt the entire root file system, you could do directory level encryption or a file level encryption using fscrypt or encryptfs mechanisms. But the fundamental concept remains the same. So moving on, how do we protect data in use? To protect data in use, there is a concept of trusted execution environment. So why do we need a trusted execution environment? If you consider the Linux kernel alone, in 2017 had 453 vulnerabilities. So any one of these vulnerabilities could potentially lead to root access on the device. And if somebody gets root access on the device, then they can potentially get access to any of the memory locations and gain control of confidential information. So to protect against that, we need a hardware isolated environment. And this is achieved using Arm TrustZone. So what it boils down to is the Arm processors, including the i.mx6, supports running two operating systems parallelly. So you have a rich operating system like Linux running, and then you can have a secure operating system which is very small, whose main focus is doing some security tasks running side by side, and the processor itself can context switch between the rich operating system and the secure operating system on the fly. So there are multiple choices available for your secure operating system, such as Opti or like proprietary operating systems like Trusty or QSEE. So what the trusted operating system can do is like have trusted applications running, handling confidential information, such as like credit card processing or verifying biometrics. So this information never has to be exposed to the rich operating system like Linux. The protection of the memory and I/O itself is enforced in hardware by the Arm TrustZone. We'll talk more about it in the coming slides. So here's like a very high-level overview of Arm TrustZone from a hardware perspective. So it has two different contexts. One is the secure context and the other one is the not secure context. So when it's running in the not secure context, it has a particular view of the system. So it has access to certain peripherals, certain memory locations. But when it switches over to the secure world context using like a assembly instruction in ARM, then it has a different view of the system. So for example, you can specify a particular memory range or certain peripherals like the security controller or the real-time clock to be accessible only in the secure context. So once it's configured in such a way that only in the secure world, it has access to these memories and peripherals. Once it switches back to the normal world, Linux does not get access to these peripherals or memory region. The secure world and normal world can still talk to each other using shared memory. And that's done in software. So a simplified software view of how the Arm TrustZone is used is in this particular figure, where you have your Linux kernel running and you have user space application running on top of the Linux kernel. It can then switch to the secure world using something known as monitor mode. And once it switches to the secure world, you have your secure operating system such as Opti running. Then you can deploy trusted user applications on top of this secure OS. And the normal world applications can still talk to the secure world applications using shared memory. So why Opti? It's an open source, tiny operating system, mainly focused on security, which helps you achieve a trusted execution environment. It supports more than 28 different platforms and SoCs. There are multiple i.MX6 boards already supported by Opti. So it's very easy to get a head start on using the Arm TrustZone and the trusted execution environment using Opti. It also has very good Yocto support. So you just need to include the Meta Opti layer and then specify which machine type or which board you plan to use. And it's going to build the operating system for you and generate the binaries. And all you have to do is load the binaries and then develop your trusted applications. So here's a high-level architecture overview of Opti. You have your trusted operating system. On the Linux side, there is an Opti driver, which was, I think, mainlined in 4.12 version of the kernel, but it has been backported to 4.9 as well by the NXP maintainer. And it also comes with the T supplicant, which is basically a daemon which is responsible for some maintenance and like accessing file storage, things of that nature. You as a customer would be responsible for writing the client application and writing a trusted application. So what are these trusted applications which we talk about? So take, for example, unlocking your phone. So you could write a trusted application to capture. So when you press the unlock button on your phone, Android or Linux can go ahead and then call this client application. And the client application can look at this, can then call the trusted application, can do a context switch and call the trusted application to do the biometrics capturing and then verification. And if the verification succeeds, it can then go ahead and unlock your phone and then hand back control to Android. This way, your biometric information never needs to leave the secure world. So even if somebody did get root access, on your Android phone, then your confidential information is not getting leaked. So there are multiple such use cases in which you can develop trusted applications and call them from your rich operating system like Linux or Android. So how do we boot this secure operating system? In case there is no secure operating system, the typical normal boot process is you have the ROM code, it loads SPL optionally, or it directly jumps to U-boot, and then U-boot loads the kernel, and everything is running from a secure context. Once we involve a secure operating system, the ROM code loads SPL, SPL loads U-boot, U-boot can then load Opti and the Linux kernel. Once it loads both of these binaries into memory, it can then go ahead and then jump to Opti. Opti would do whatever initialization is required in the secure world and then do a context switch to the normal world and then hand control over to the Linux kernel, which would then continue the boot process. And then whenever the Linux kernel needs to avail services from Opti, it would have to context switch back to the secure world. And then data can be shared back and forth using like pointers and common memory, which is accessible both by secure world and the normal world. There are very good examples available on how to quickly get started with writing a trusted application. So you can take a look at the Linaro GitHub page for examples. There is also a concept of trusted storage. So in case like Opti does want to store data into non-volatile memory, it can either store it in encrypted format in the Linux root file system, or it can also write to the eMMC RPMB partition, which is like a protected partition which prevents unauthorized access. So the next topic is trusted platform modules. So we talked a lot of features, security features available on i.mx6. In case you're looking for more advanced features which are not offered by i.mx6, in that particular case, you can go for an external security chip, which is dedicated for protecting secrets, verifying the integrity of the platform, and can also do device identity. But the main use case for TPM chips is like for storing keys and certificates. So there are FIPS certified TPM chips readily available. So if in case you didn't want to go through the FIPS certification process for the encryption algorithms available on i.mx6, then you could go for a FIPS certified TPM and then make use of that for key storage. There are many modules available from Infineon, Microchip, ST Microelectronics. Most of these modules talk to the host processor or I2C or SPI. Those are the two commonly used protocols to talk to the TPM chips. And depending on the TPM chip, it can offer multiple features such as device authentication. A lot of other features are mainly focused on certificate management, key management, which are used for features such as like secure updates, verifying the integrity, establishing secure network communication. Additionally, some of them have like hardware random number generators and secure real-time clocks as well. So depending on what functionality you're looking for, you can appropriately select a TPM chip. So here's the typical use case for a TPM chip. Let's say you have an embedded device running a web server, and you have clients trying to connect to the web server, and the client wants to authenticate the server, in which case you need to store certificates on the server, and you also need to, you probably have a private key on the server. So this particular certificate and private key needs to get protected. And to do so, you can use like a TPM chip, which has built-in non-volatile memory to store the private key onto the device. And once you store that, you can ensure that the key never leaves the TPM. You can make use of that particular, you have APIs available to perform functions such as like signing, encryption, decryption using the key, or by sending commands over the I2C or SPI interface. So that way the key is always protected. You can also prevent unauthorized use of the key by a concept called as sealing. What sealing does is during the boot process, let's say you have U-boot can compute a hash of itself and capture a state of some of the hardware registers and then send it over to the TPM chip. And once U-boot loads the Linux kernel can do the same and extend these hashes. And these are stored in a register called PCR register on the TPM chip. And as these hashes get extended, your user space application, once it boots, it can then go ahead and then request a sealing of the key. So in case next time when the device boots, if the bootloader is replaced or if the kernel is replaced or something changes in the application, then these hashes do not match, in which case the key does not get unsealed and nobody can use the key for unauthorized access. In order to start using the TPM, you need additional software. You need to enable the appropriate driver. Most of the TPM modules nowadays do have good mainline support in terms of driver. You also need to additionally configure your device tree to enable the SPI or I2C node to make use of the driver. And then lastly, you need to include certain tools like TPM tools, or if you're trying to use OpenSSL, OpenSSL has a TPM engine module available. So you have to enable that as part of your Yocto build to make use of these TPM features. So in today's webinar, we kind of covered an aspect of secure by design by hardening the system, by encrypting the data, both at rest, in use, and in motion. The key takeaways for today's webinars is encrypting data is fundamental to protecting the IP and user data confidentiality. i.MX6 processor and Advantech hardware already has these features freely available to you. It helps you do secure key storage. The Arm TrustZone feature is available in case you want to deploy a trusted execution environment. You have support for hardware accelerated crypto algorithms. And making use of each of these hardware features, you can add an additional layer of security for free on your product. Lastly, in case you want to add even more additional security features, you can always go for an external chip such as TPM. I think that's it for the slides. I'll hand over the presentation to Teresa.
Thank you, Akshay. And thanks, Mache and Jason, for another great session around securing embedded Linux devices. Man-in-the-middle attacks and protecting sensitive data, especially when it comes to user data, is obviously a hot topic these days and of primary importance. So I'm glad we could collaborate to bring this session to our audience. We have some really good questions that I'm seeing that have been posted here. So let's go ahead now and we'll open things up with the Q&A. The first question that I see is there any performance impact to encrypting the RFS?
I'll take that question. There is some performance impact when you do encrypt the root file system, depending on if you plan to use hardware accelerated algorithms or not. So when you encrypt your root file system, there is a tool called crypt setup, and the crypt setup has various options as to which algorithm needs to be used for encrypting the root file system. So I would just make sure you pick one which is like hardware accelerated, the one which I.MX6 supports, and in which case any performance impact would be minimal. In terms of boot time, since you're adding like a initramfs to unlock the root file system and mount it, it adds around approximately 2 seconds of additional boot time.
Thanks, Akshay. And that was a great question. The next question I'm seeing is, in the secure boot process, do we scan other resources as well, which are open for access?
The short answer is yes. The long answer is it depends on how it is being implemented. So in last week's webinar, we talked about secure boot and chain of trust, in which the ROM code verifies the signature of the bootloader. The bootloader then goes ahead and then verifies the signature of the Linux kernel, and the Linux kernel can verify the signature of the root file system using like dm-verity. Similarly, if you are using like Opti, then depending on if SPL is loading Opti or if U-boot is loading Opti, you would need to sign Opti using the NXP code signing tools, and then ensure that U-boot verifies the signature of Opti before jumping into Opti. And there are standard APIs available in U-boot to do that. So as long as that's implemented, it should, the entire chain of trust should be established.
Great, thanks Akshay for that answer to that question. Another question here that we've received is Opti fully open source?
Machi, do you want to take that?
Certainly. So Opti is open source. You can find the Opti implementation in Yocto. There is a specific meta Opti, which holds the open source, the implementation of Opti, and you have full access to the source code. And as Akshay showed today in a slide, there are of course alternatives to Opti, which are non-open source, which are proprietary, but Opti is available as an open source project.
Great, thanks for that answer, Mache. Let's see, next question. Is TrustZone a TPM? What's the distinction between those terms?
TrustZone is not a TPM. So TrustZone is, so TPM is a standard defined by TCG, which is used for, which has a specific set of APIs to perform security functions. Whereas TrustZone is hardware technology by Arm, which can help you implement a trusted execution environment. On top of the trusted execution environment, you could potentially run a software TPM which complies to the APIs defined by the TCG group, such that like your secrets are not leaked, and then like using these standard APIs, the Linux kernel can treat the software running on the TrustZone similar to external TPM, but they're not one and the same.
Great, thanks, Akshay. And related to the question, TCG, what does that mean? Or what does that stand for?
TCG stands for Trusted Computing Group.
Okay, great. Oops, let me get through this. The questions keep coming in. Is opte small enough to run from internal memory?
It depends on what features are enabled in opte. So opte has a lot of drivers and modules or configuration options which can be enabled for secure data storage, trusted UIs, so on. So depending on which features are enabled, your code size can vary. I think the standard out-of-the-box size is around 256 kilobytes. It's a tiny operating system, but you can go ahead and then strip features to probably get it down to like 120 KB or so, in which case it might fit inside the internal RAM.
Great, thanks, Akshay. Let's see, we have another question. The questions keep coming. We have a few more minutes, so please, if you do have more questions, feel free to ask them. Next question, can you have multiple trusted applications running at the same time in opte?
The answer is yes. So you can have, if you have a multi-core processor, you can have multiple trusted applications running at the same time.
Great, thanks, Akshay. And let's see, we did have another question. Are the slides available to review? And I can answer that question. Yes, everyone in attendance, or actually everyone who has registered for today's session, will receive an email. I'd say within 24 hours, you'll receive a link to the recording, as well as a link to the PDF of the slides that you can download, and as well as contact information, email addresses for any of today's presenters, so that if you do find that you have a question after today's session has ended, you are welcome to contact any one of the presenters to ask your question. And I don't see that we've gotten any more questions. So we have a few minutes left. I don't know, Mache, Akshay, Jason, if there's anything additional you'd like to add before we go ahead and wrap things up.
I guess it's no.
No? Okay. Well, it was a good session, a lot of good information and a lot of great questions. So I'm amazed that we were able to fit all of this information into a 1 hour session. So it's a good thing. So since we're just about out of time, I guess we'll go ahead and wrap things up for today. On behalf of myself, Mache Halish, Akshay Bhatt, Jason Zhu, I want to thank you all again for being online with us today. We'll hopefully see you again in 2 weeks for session 4. We have 2 remaining sessions. next week, or 2 weeks from today, session 4, security in production, updating and deploying software OTA securely. And with that, I'll go ahead and sign us off, and I hope everyone has a good day. Thanks again.
Thank you all. Bye-bye.
Bye now.